Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will tell you our lecture on theory of numbers. Lecture number 34, in which I will solve some problems of Wilson's theorem. Now we solve a problem. Problem is prove that factorial 28 plus 233 is congruent to 0 modulo 899. Now we solve this. We will solve this problem with the help of Wilson's theorem. In Wilson's theorem, we know that if P is a prime number, then factorial P minus 1 is congruent to minus 1 modulo P. This is number 1. Since 899 equal to 29 multiply 31. Here 29 and 31 both are prime numbers. Therefore 29 minus 1 factorial is congruent to minus 1 modulo 29. Implies that factorial 28 is congruent to minus 1 modulo 29. This is number 1. Since 233 equal to 29 multiply 8 plus 1. Therefore, if we divide 233 by 29, we get remainder 1. Therefore, we may write 233 is congruent to 1 modulo 29. This is number 2. Adding 1 and 2, we get factorial 28 plus 233 is congruent to minus 1 plus 1 modulo 29. Implies that factorial 28 plus 233 is congruent to 0 modulo 29. This is number 3. Again, since 31 is a prime number, therefore, by Wilson theorem, 31 minus 1 factorial is congruent to minus 1 modulo 31. Implies that factorial 30 is congruent to minus 1 modulo 31. Implies that 30 multiply 29 multiply factorial 8 is congruent to minus 1 modulo 31. Implies that 30 means 31 minus 1, 29 means 31 minus 2, multiply factorial 28 is congruent to minus 1 modulo 31, implies that 31 square minus 3 multiply 31 plus 2 multiply factorial 28 is congruent to minus 1 modulo 31. Here we see that 31 square is divisible by 31. Also 3 multiply 31 is also divisible by 31. So we may remove these two terms and we may write 2 multiply factorial 28 is congruent to minus 1 modulo 31. This is number 4. Since 31 divides 465, therefore if we divide 466 by 31, we get remainder 1. Therefore we may write 466 is congruent to remainder 1 modulo 31, implies that 2 multiply 233 is congruent to 1 modulo 31. This is number 5. Adding 4 and 5, we get 2 common. Here factorial 28 plus 233 is congruent to here minus 1, here plus 1 modulo 31, implies that this minus 1 plus 1 is 0. So we may remove 2 as GCD of 2 and 31 is 1. That means factorial 28 plus 233 is congruent to 0 modulo 31. This is number 6. From 3 and 6 we get factorial 28 plus 233 is congruent to 0 modulo LCM of 31 and 29. LCM of 29 and 31 implies that factorial 28 plus 233 is congruent to 0 modulo LCM of these is 899. So proved. Now we solve the next problem so that factorial 10 minus 32 is congruent to 0 modulo 13. Now we solve this. Since 13 is a prime number, therefore by Wilson theorem factorial 13 minus 1 is congruent to minus 1 modulo 13, implies that factorial 12 is congruent to minus 1 modulo 13, implies that this equal to 12 multiply 11 multiply factorial 10 is congruent to minus 1 modulo 13, and 12 means 13 minus 1, 11 means 13 minus 2, multiply factorial 10 is congruent to minus 1 modulo 13, implies that 13 square minus 3 multiply 13 plus 2 multiply factorial 10 is congruent to minus 1 modulo 13. Since 13 square is divisible by 13 and also 3 multiplied by 13 is divisible by 13. Therefore, we may remove these two terms and we may write 2 multiply factorial 10 is congruent to minus 1 modulo 13. Let this is number 1. Now, since 64 is congruent to minus 1 modulo 13, because 65 is divisible by 13. So, for making 65, here we have 64, so 1 is less. Therefore, that is minus 1 is remainder. Implies that 2 multiply 32 is congruent to minus 1 modulo 13. This is number 2. Subtracting 2 from 1, we get 2 under bracket factorial 10 minus 32 is congruent to minus 1 minus minus 1. Modulo 13 implies that 2 multiply factorial 10 minus 32 is congruent to 0 modulo 13. Since GCD of 2 and 13 is 1, therefore we may transfer this 2 here by 0 by 2. Implies that factorial 10 minus 32 is congruent to 0 modulo 13. Proved. Now we solve the next problem. So that 2 multiply factorial p minus 3 plus 1 is a multiple of p when p is a prime number. Now we solve this. Since p is a prime number, therefore by Wilson's theorem, factorial p minus 1 is congruent to minus 1 modulo p. Implies that p minus 1, p minus 2, factorial p minus 3 is congruent to minus 1 modulo p. Implies that p square minus 3p plus 2 multiply factorial p minus 3 is congruent to minus 1 modulo p. Since p square is divisible by p and also 3p is divisible by p, therefore we may write this implies 2 multiply factorial p minus 3 is congruent to minus 1 modulo p. This means p divides this minus minus 1. 2 multiply p minus 3 factorial plus 1. Therefore, 2 multiply p minus 3 factorial plus 1 is divisible by p. Proved. Now we solve the next problem. Problem is using Wilson's theorem, find the least positive residue of 48 multiply 49 multiply 50 multiply dot 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 multiply 91 multiply 92 multiply 93 modulo 47. Now we solve this. Since 48 is congruent to 1 modulo 47, because if we divide 48 by 47 we get remainder 1. Similarly, 49 is congruent to 2 modulo 47. Dot 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 92 is congruent to 45 modulo 47, because if 92 is divided by 47 we get remainder 45. 93 is congruent to 46 modulo 47. Let these are number 1. Multiplying these we get 48 multiply 49 multiply dot 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 multiply 92 multiply 93 is congruent to 1 multiply 2 multiply 3 multiply dot 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 multiply 45 multiply 46 modulo 47 implies that 48 multiply 49 multiply dot 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 multiply 92 multiply 93 congruent to factorial 46 modulo 47. Let this is number 2. Since 47 is a prime number, therefore by Wilson's theorem factorial 47 minus 1 is congruent to minus 1 modulo 47, implies that factorial 46 is congruent to minus 1 modulo 47. This is number 3. From 2 and 3 we we get here 48 multiply 49 dot 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 multiply 92 multiply 93 is congruent to factorial 46 modulo 47, and here factorial 46 is congruent to minus 1 modulo 47. Here we see factorial 46, here in left side factorial 46. So we may write 48 multiply 49 multiply dot 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 multiply 92 multiply 93 is congruent to this minus 1 modulo 47, implies that 48 multiply 49 multiply dot 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 multiply 92 multiply 93 is congruent to this minus 1, means we may write 46, 1 less than 47, modulo 47. Therefore, remainder is 46. That means when we divide these 48 multiply 49 multiply dot 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 92 multiply 93 by 47, we get residue 46. This is the answer. Now we solve the next problem. Problem is using Wilson's theorem for any odd prime p, prove that 1 square multiply 3 square multiply 5 square multiply dot 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 p minus 2 whole square congruent to minus 1 to the power p plus 1 by 2 modulo p. Now we solve this. Since p is congruent to 0 modulo p, because p minus 0 means p is divisible by p. This is number 1. And k is congruent to k modulo p, because k minus k equal to 0, which is divisible by p. This is number 2. Subtracting 2 from 1, we get p minus k is congruent to 0 minus k modulo p, implies that p minus k is congruent to minus k modulo p. Let this is number 3. Putting k equal to 2, 4 dot 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 p minus 3 p minus 1, we get, firstly we put value of k is 2, that means p minus 2 is congruent to minus 2 modulo p. For k equal to 4, p minus 4 is congruent to minus 4 modulo p dot 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 dot. For k equal to p minus 3, p minus 3 is congruent to minus p minus 3 modulo p. Putting k equal to p minus 1. We get p minus 1 is congruent to minus p minus 1 modulo p. Multiplying all these, we get, here we see that p minus 1 means 1. Here p minus 3 means 3. Multiply p minus 4, p minus 2 congruent to, here minus 2 multiply minus 4 multiply minus p minus 3 multiply minus p minus 1 modulo p, implies that 1 multiply 3 multiply p minus 4 multiply p minus 2 congruent to, here we see minus, here minus, here minus, here minus, means we get minus 1 to the power p minus 1 by 2, and then 2 multiply 4 multiply p minus 3 multiply p minus 1 modulo p. Let this is number 4. Multiplying both sides by 1 multiply 3 multiply p minus 4 multiply p minus 2, we get 1 square multiply 3 square multiply p minus 4 whole square p minus 2 whole square is congruent to minus 1 to the power p minus 1 by 2, and here if we multiply 1 multiply 2 multiply 3 multiply 4 p minus 4 multiply p minus 3 multiply p minus 2 multiply p minus 1, that means factorial p minus 1 modulo p. Let this is number 4. By Wilson's theorem, for p to be a prime number, factorial p minus 1 is congruent to minus 1 modulo p, implies that minus 1 to the power p minus 1 by 2 multiplying both sides, factorial p minus 1 congruent to minus 1 multiply minus 1 to the power p minus 1 by 2 modulo p, implies that minus 1 to the power p minus 1 by 2 multiply factorial p minus 1 is congruent to minus 1 to the power p plus 1 by 2 modulo P. Let this is number 5. This is 5 and this is 6. From 5 and 6, we see that in right side here minus 1 to the power p minus 1 by 2 factorial p minus 1. In left side here the same thing. So from 5 and 6 we get here left side 1 square multiply 3 square multiply p minus 4 whole square multiply p minus 2 whole square is congruent to minus 1 to the power p plus 1 by 2 modulo p, and proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.